Hi everybody, welcome back to Chem 161. Let me wind the music down here. What are we doing today? We are doing more Chapter 1 stuff, and I'm going to talk a little bit about Lab Number 1 later on in the class once we've gotten some more of the content for the course under our belt. Because we got to talk about math and how to measure stuff, and this will probably still all be reviewed. Chapter 1 is a review chapter after all. We hit a little bit of new stuff in Chapter 2. But today our objective is to talk about how to measure anything, how to get the correct number of significant figures when measuring anything, and then how to do calculations with these numbers that we generate. So whenever we are working in a laboratory setting, such as, I don't know, maybe the classroom, or more likely and more appropriately, your workplace in the future, you're going to need to measure stuff. And there's going to be various reasons that you're going to need to measure stuff. Maybe you're working in a pharmaceutical company and you're in charge of synthesizing, I don't know, vaccine. And you need to weigh out specific amounts of reagents so you get the starting material prepared or whatever. So you'd have to weigh that out. Or maybe you are working as a civil engineer and you need to make sure that all of the parts of the bridge that you are constructing fit within each other as depicted on the blueprint. And you don't want them to be... You don't want the tolerance on the length of the girders and the beams and stuff like that to be off, because then they wouldn't fit and you'd have to grind them down, or there would be too much of a gap or things like that. So you're going to need to acquire numbers and units, and you're going to need to be able to manipulate those in a competent way that not only you understand, but also the people that are working with you and around you will also be able to interpret. So we're going to define a measurement as any quantity that has two parts. And those two parts are a value and then the units, which are on the next slide. And so we'll just write that here. Value and units. So having only one doesn't do anything. If you tell me that this post that I'm making a fence out of is meters long, that doesn't help me. Likewise, if you tell me that I need to drive 17 to get to work, that doesn't mean anything. 17 what, right? We're going to be making measurements with all sorts of different tools, and their use and degree of flexibility and their amount of error that they introduce depends on the nature of the tool. So we're going to be discussing a lot of that today. Here's our argument that we're going to make in terms of units. If you see the sign, to a scientist, this sign means nothing. 65 what, officer? I was going 65 feet per second. It's like 120 miles an hour or something like that. That will not hold up in court, by the way. I've tried. But to a scientist, this number does not mean anything. If I were to write this on a piece of paper and then hand it to my advisor, who would then pass those notes to manufacturing, they would look at my numbers and be like, well, we don't know what to make this dimension. Like, what are we supposed to do? This has come up in the real world, obviously all the time for students, but like even as high up as NASA, there was a Mars probe. I don't remember when this was, but somebody did all their calculations in imperial units, and the intent was that they were supposed to be in metric because the formula was programmed in metric or something like that. And the probe crashed into the planet, and there went hundreds of millions of dollars because some dumbass didn't convert meters to feet properly. I shouldn't call somebody at NASA a dumbass, but when you make a rookie mistake like that, sorry, dude, you're a dumbass. We're gonna define these units, the most important part of the measurement, as miles, or not miles per hour. We're gonna define those as units. Always include the units, except, and this is infuriating to me, except when entering numbers on Canvas. When you are dealing with Canvas and interacting with the quiz module and typing in your answers, all of the answers that Canvas will request will expect a number. And if you try and type in the units there, it will blow up. It just is like a unit or a number was expected. Please type only numbers. And it won't let you type units. So you can't type 65 miles an hour. It would expect 65. And that drives me insane because the whole point of this class is for me to make sure that you understand units. So on tests and assessments and stuff like that, unless very specifically instructed, don't put the units in, just the number. I will say something along the lines of give your answer in kilograms per liter or something like that. And then you need to give me the correct number with the assumption that you would have tacked that unit on the end. In your laboratory, that's a little bit different. And we're going to talk about that when we talk about the lab after the break today. I'm sure that there are tons of cringe things that NASA has done, but that's the one that I'm most aware of, is that, yeah, we blew up a probe because somebody did Imperial and it was supposed to be metric. Speaking of Imperial, the Imperial system of units is the worst thing ever. Here are some numbers from this system. They don't make sense. Who chose these numbers? 12 inches in a foot? What? Why not 10? Why 12? Why not 12.5? Like, doesn't make sense. 3 feet in a yard, we only have 2 feet. I don't even want to try this one. Like, it's just, it's stupid. In fact, it gets worse. And I always forget that I need to have this on screen when I do this. Hold on. I gotta find which window is the stream. There we go. So, Imperial Units flowchart. And I both love this flowchart. I love that it exists, and I also hate it. All right, so I'm going to show you all of the different units for length. If I can find the flowchart, where is it? There it is. All right, so window capture, Wikipedia. Boop. There we go. So these are just units of length. And it keeps, oops, that actually isn't helping me scroll. Oh, that's because that's the end of the picture, so. It keeps going further down, like if I do this, there's more to it down here, but yeah. I would like you to tell me how many barleycorn there are in 744 Gunter's chains. Like, what the deuce, right? This is the stupidest thing ever. Like, the empirical system can just go fuck off. Like, no. We're not going to deal with that shit. We're going to do metric system because the metric system is super, super convenient. Everything's based on a power of 10, which means that these are numbers you can commit to memory, and you don't have to look on a stupid chart all the time. Because nobody in their right mind, other than maybe like Ken Jennings, because he is a trivia goddess. I'm gonna misgender him. He's a trivia god, and he probably knows all the conversions for all of these things. But we don't need any of those. We just need to have a basic unit, and then modify that. And that's what the metric system does. It's super useful for that. And yeah, I would believe that people could measure with just using like one simple tool and then themselves. In fact, I think like the cubit, which is an ancient civilization's measure of the pharaoh's forearm length, like from his elbow to his fingertip. Like that was a unit of length. But the problem that you run into there is that everything is different, and that's not super useful. Like my arms are not going to be the same length as your arm, for example, because I'm tall and round. So my arms, I don't know what any of that has to do with my arm length, whatever. I'm highlighting some prefixes here and some numbers. And those two things, I guess I could connect them with a line here. These are going to be related to each other. So whenever you see milli, you should think 10 to the minus 3. Whenever you see kilo, you should think 10 to the positive 3. And whenever you see centi, you should think 10 to the minus 2. So we're going to be applying these prefixes to various units that I'm going to briefly talk about in the next few slides. But you've probably seen them before. So these are the units that we're going to be working with in this class. Aside from the two at the bottom, those two exist. We are going to use the ampere at some point in 163 when we talk about electrochemistry. So we're going to talk about batteries and how to conduct current and how much energy you can get per volt and things like that. Or not per volt, but per coulomb at a given voltage. So the ampere is something that we'll come back to, and we'll define it later. It's a joule per second. No, that's not right. That's watts. Maybe it is a joule per second. Yeah, something like that. We're not going to deal with it right now. I usually derive the unit anyway for you guys. But these other units that we're going to use are very, very useful. Oh, it's coulomb per second. That's ampere. Sorry. So I'm going to just talk about these on the next few slides because I have a slide dedicated to each of them with some interesting facts as to what is the definition of a meter. Well, it's actually changed very recently, and my slides will talk about that. But this slide right here is actually really important. These are the metric prefixes that we're going to be using in chemistry, and we actually use all of these up to about mega. Like, we actually use femto. Femtoseconds are the amount of time it takes for a molecule to, like, jiggle or wiggle or vibrate or rotate or something like that. Pico is useful for the interatomic distance between two atoms, so you can measure that in picometers. Nanometers we're going to use in this class. We're going to use it for light. That's chapter 3. Micro, milli, centi, deci, kilo, those are things that we can actually measure. So you might be measuring something in microliters at some point. Really tiny amounts to make like very small amounts of solution. That is a thing that you would do. Not just in this class, but in like maybe a chemical prep or medicinal prep or something like that. And then mega, giga, tera, those tend to be used for things for like hard drives or your processor, how many cycles per second it can do. And that's a rough approximation, of course, because processors and stuff are powers of 2, and the metric system is powers of 10, but it roughly equates to about that much. So that's where those terms are going to be coming up the most. Now, we're going to assign the number that you see in a row with the prefix that you see there. So, like, here's micro right here. And so what this means is that if we're going to write a statement that relates these two things, I'm going to make an equality. And the rule for all equalities is both sides have to be equal, right? So I have to put these on different sides of one another. Where did my cursor go? There it is. So this has to go over here, and this has to go over here. And then I just have to put m on both sides. M, m. There you go. It's done. So one of these things is 10 to the minus 6 of those things. So this is how you construct statements out of this table. Is it's got to be equal on both sides, right? So put the number on both sides. The symbol is just another way of writing the number, right? So let's do that for pico. So a picometer would be 10 to the minus 12 meters, and we'll just put the meters in. And then I'm going to put a 1 for clarity. So you can make any relationship however you want to this way. And if you do it this way, and just remember, put all of the information on opposite sides so that you have an equality, you'll never mess it up. You'll always construct it correctly. I know that was a real challenge for me when I was starting out, was like, where do the numbers go? Where does the prefix go? Well, just, they have the same value, right? So you need to have them on opposite sides of the equal sign. Otherwise, it's not equal. And when I thought of it that way, I was like, oh, that's really obvious. But nobody ever says that. So there you go. That will be helpful for you. All right, let's talk about length, just in more detail. A meter is defined as the amount of distance light travels in this amount of time. 299792458 to the negative 1 seconds. That is such a silly thing, but we wanted to define length on a physical constant. Now, That's unfortunately very difficult to do when physical constants are mostly from things that we've constructed and they're therefore inaccurate. But light is a super useful resource because light in a vacuum moves at the same speed. It's a universal constant. So our hands are sort of tied there. That's what we've chosen to do there. Now, a meter is a very long distance relative to things like, say, an atom, or maybe this paper clip that you're trying to weigh or measure or whatever. So using a meter is not super practical. We're going to be using centimeters and millimeters for objects that we can manipulate in the laboratory. And then we're going to go even smaller. We're going to go down to picometers and nanometers, like I said, for things that occur in the atom themselves. So like bonding or electronic absorption or emission, aka light. I actually don't know what the unit of mass has changed to, but the standard for mass used to be this cylinder that they kept in the Louvre. I want to say it was the Louvre. And that cylinder was kept in like a chamber, sealed off with argon, and they said this is 1 kilogram. And they probably had like a light shining on it from I don't know, science, a holy science light with a choir in the background at all times, or something silly like that. But what they found out was that over time, that standard would change mass very, 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 very slowly, like at the 12th or 13th decimal point. And so that's obviously no good if your standard is a physical construct that isn't constant. So I actually don't know what it was changed to. There was an article about this, which is why I actually wrote that statement there. It's recently changed. But if you're curious, you can go look it up and see what the current physical standard is for mass. And I want to say that it's also based off of light because we're trying to base this off of things that just exist. Relation to atomic after the observation of the changes. That doesn't ring any bells to me, unfortunately. That actually makes me think of time, which we're going to talk about in a second with cesium-131 transitions. We all know about temperature because we've all been way too cold the last few months, and looking outside, it's finally a nice day. We're going to use this unit in this class the most, Kelvin. Actually, in reality, we're not going to use Kelvin at all because we're not going to get to a formula that actually uses it just yet. But in 162, when you talk about gas laws, or when you start doing enthalpy or thermodynamics, we need to use Kelvin. The reason for that is because any formula that you use that has temperature in it, you could rearrange potentially so that the temperature is on the bottom, and if you input a temperature that has a value of 0, which totally exists, that will ruin your equation. You'll destroy all the mathematical universe. Oh, it's based on Planck's constant. That does sound familiar. Okay. I'm going to have to look that up during the break because I find it interesting, but I just don't remember. So we're going to be using Kelvin. The formula between Celsius and Kelvin is just this. And you can always just look this formula up online. In fact, if you just type it into Google, say like, what's 74 Celsius in Kelvin? And it will be like, oh, that's 344 or whatever. The number of decimal points that you need will affect the number of sig figs of your answer. So if you measure Celsius in 22, like say like this is your result, you only need to go to this decimal point because anything past it isn't going to get kept anyway, due to how addition works with sig figs. So now there is an imperial unit of temperature that's dumb. We're not going to use Fahrenheit. If you have Canadian friends, though, it's really good for confusing them. My best friend who lives in Ontario, Canada, we talk about the weather often, and I'm like, yeah, it was 67 today. And he's like, holy shit, that's hot. Because he operates in Celsius, and 67 would be like 137 degrees or something absurd like that. So There's a cat here. She wants to say hi, but we're busy. How do we define time on a physical thing? Turns out that if we collect cesium atoms, and it's a specific isotope of cesium, I want to say it's 131. But there's a very specific transition of electrons when you excite it, and if you count off an exact number of those transitions, we define that as a second. And so that's where the device called the atomic clock comes from, is that we have a sample of atomic cesium in there, and there is a sensor that is detecting the number of emissions that pass, and when it sees that many emissions, it goes boop and it increments a second. And it turns out that that's actually a very, very, very specific unit of measure, and so that's great. That's a physical thing that we can base something off of, because cesium's not going to suddenly slow down or speed up. It just, cesium is a constant. It's just, it is what it is. I love these stories I'm seeing in chat. I had no idea about the Fahrenheit one. Like, that makes sense that, like, humans would be at 100 degrees Fahrenheit instead of 98.6. That's really funny if that's true. That does sound like a legend, but I really want that to be true. All right. Volume is not technically an SI unit, but we are going to be working with volume a lot. So this unit right here, cubic meters, not super useful because a cubic meter is huge. Imagine a meter stick, like you have the end on the ground and you're holding it in your hand, so it's like orthogonal to the ground. And then imagine like you let that fall flat on the ground and then rotated that 90 degrees to kind of make a sort of like axes out of your meter stick. That volume that those axes would fill would be a 1 meter cube, and that's a humongous volume. Like, we're not going to be able to measure any liquids in the laboratory in cubic meters because we just get this really teeny tiny decimal. So cubic meters not super useful. The liter is much more practical. What is a liter? A liter is a 10 centimeter cube. Now, technically, this would be a decimeter. So 1 cubic decimeter is a liter. But that's kind of silly to work with cubic decimeters when centimeters are much more common. And when we do that, you get 10 times 10 times 10, which is 10 cubed. Cubic centimeters is a liter. And if we know that there are 1,000 milliliters in a liter, we can just divide this by 1,000 on both sides, and then we end up with this. And this is super useful for us. Keep that conversion in mind, because for density, we're going to be using that quite a bit. 1 cubic centimeter is a milliliter. All right. Oh, speaking of density, here's some density problems. We haven't actually defined sig figs and stuff yet, so we're not going to worry about that a ton. But we will talk a little bit about density, because we're going to be measuring some stuff in a future lab, and we'll need its density in order to do some calculations. So density is probably the simplest relationship that we talk about in this class. So a milliliter is only a gram if the substance is water, and also that substance is water at 4 degrees Celsius. So that relationship is not going to be super useful to you. Mass and volume are related by density, but there can be any relationship. So for example, water at room temperature is about this many grams per milliliter. So if you had a milliliter of water at room temperature, you'd actually have very slightly less than a gram. And the reason for that is because density is a function of temperature. As you heat things up, they expand and their density goes down. You can kind of test this by, like, if you put a little bit of cooking oil in a pan, you would know what mass of cooking oil was in there because it would be constant. But then when you heat it up, it spreads out and its volume gets much, much bigger. But its mass remains the same because you haven't added any oil, so its density would go down. There's all sorts of applications for density that we're going to be using, but the basic one that we have here is density is mass divided by the volume of the object that you're measuring. Room temperature is, the standard is just, I believe in physics it's 25 degrees Celsius. That's actually a little warm for room temperature. At least it's warm for me. When we look at various substances, we're going to be measuring their densities in various units. Solids get grams per cubic centimeter only because solids can be formed into cubes fairly easily. Liquids are always grams per milliliter because you cannot cube a liquid unless you pour it into a perfectly cubical container. The liquid's just going to occupy whatever volume its container has. So we use these specific units, but keep in mind, centimeters cubed and milliliters are the same thing. So if you give the density of a solid as grams per milliliter, that's totally fine. Most reasonable people would be able to interpret that. Now, for gases, we need to actually make a larger volume because there's just so little matter in a liter of a gas. For example, the density of air is like 1 or 2 grams per per liter. It's not that much because there's just not that much matter in the air. Most gases have very low density on this scale. So we're going to keep that formula handy, and we're going to do some mathematical calculations. Since it's a formula, if I give you any two things, you could then solve for the third one. That's trivial to do as long as you are able to manipulate the algebraic expression. So let's do a few problems with that. Oh, yeah, and then last we have this fun fact. If I have two things with different densities, the lowest density floats. Do I have the density column video? I might as well show the density column video because it's just really neat to see this. YouTube. Density column. Yeah, here we go. I mean, you can't see it. It's playing music, though. Alright, that's what I want to see, but I'm going to have to fiddle with it. Oh, maybe I won't have to fiddle with it. Look at that. You don't need this at the bottom. There we go. Alright, so this density tower has a bunch of stuff in it, including safety. So these are the liquids that are used. And then we're going to drop some solids in there too. Not the turkey baster. That's going to be used for making the column. You do not need adult supervision for this. Don't be ridiculous. Alright, there's our substances. We're going to stack these in this order with the honey on the bottom and the lamp oil on the top. And what we've done is we've set them up such that they are arranged in order of their density. So the honey will be on the bottom, then the corn syrup will sit on top of that, the maple syrup will sit on top of that, and so on and so forth. And we've also tried to select them in such a way that we have alternating solubilities. For instance, water is very insoluble in vegetable oil, and rubbing alcohol is very insoluble in vegetable oil, but rubbing alcohol and water are extremely soluble in each other. So we have separated those out so we don't just get a mixture. The others are just so viscous that you can pour one on top of the other, and as long as you don't stir it really readily, they won't mix. So we're going to just pour these in here. Here we go. And then when you drop in the objects, you get some mixing, obviously. But what you notice is that the things start to sink to a specific level, and then they just hang out there. There we go, that's what I'm looking for. And there's the density column. So we have sorted these, I'm trying to count them really quickly. 3, 7, 10, 13. These 16 objects have sorted by their density. The bolt is the most dense, so it's sunk all the way to the bottom. Then the honey is the next most dense, then corn syrup, then the popcorn kernel. Maple syrup, dice, milk, dish soap, cherry tomato, water, beads, vegetable oil, soda cap, rubbing alcohol, lamp oil, and the ping pong ball, which is full of air, so it's going to float on the top. So that's kind of cool that you can put all of these different things in there. You may have seen thermometers that have these like little floating balloons in like a column of water, and those are density columns. As stuff heats up from temperature changes, the water that the stuff is in also heats up and its density changes. And then the little balloons that are inside the thing will either float or sink based on what the temperature is. How dense is it is in one adult supervision? I'm trying to think of something witty, but you're going to have to get back to me. I wasn't prepared for that one. I don't know, 35 don't do that's per mom or something. All right, so here's a very, very simple density calculation. So let's suppose you put olive oil and water into the same container and they don't mix. You're going to use this much olive oil, 18.6 grams and 20 milliliters. And you're going to use 25 grams and 25 milliliters of water, which floats based on the calculation. So very quickly, do the density calculation for each of these substances. And then tell me the order in which they would float if you were to draw them on a piece of paper. Yeah, those temperature things are really popular. I know a lot of physicists have them because they like to talk about density and then use that. Lava lamps operate by the same principle. The blobby medium, or the lava, sinks to the bottom as it cools, and then it gets near the heating element and it heats up, and then it goes back up because its density is lower. So if you were born in the 70s, you know all about density columns. Just a sign of the times, I guess. All right, do those calculations and I'll be right back. All right, once you have your answer, which one floats on top, type it in the chat for me, and then we'll go over the answers together. All right, so let me zoom this in really quickly here. Oops. So let's write down the formula for density. And so I know the mass and the volume for each of these, so we could just do the calculations as so. I actually know a lot of people that have lava lamps. Now, we haven't actually done sig figs yet. We're going to do that later today. But hopefully you know that you should have 3 sig figs for your answer because we're doing division and all of the other components had 3. But that's the density of the oil. And then if we do the density of the water, we'll divide its mass by its volume. And we get 1 gram per milliliter. And so the conclusion that we would get is that the density of the oil is less than the density of the H2O. Make sure you're using the correct symbol. We're going to be using this symbol a lot in this class. The alligator eats the bigger number. And so if we were to draw this out, our container would look like this, with a layer in the middle, and on top would be the oil, and on the bottom would be the H2O, no matter how much of it we put there. So if there was a lot of oil and only a little H2O, same thing. The density is what we care about. All right, lower density goes on top. All right, I'm going to give you some more complex calculations for density. Oops, I didn't mean to flip past it. So in this instance, what I want you to do is observe these conditions. So I have a block of copper. Here's its mass. And I'm going to put in a graduated cylinder that already has 75 milliliters of water. And the volume of the water changes once I've put the copper block in there. What's the density of the copper? And if the copper is a perfect cube, what would its edge length be? Well, what's the formula for a cube? So the volume of a cube is whatever its length is, cubed. So there's your formula that you'll need for that. Go ahead and try these calculations, and when you get your answer, type it in the chat. And until then, Maya is going to meow at you. Say hi. Say hi. Tell them the answer. She doesn't know the answers, it turns out. All right, I'll leave you guys to do your calculation, but let me know if you have any questions in the chat. All right, 1 or 2 more minutes, and we'll go over the answers together. I'm trying to get her to talk, but it's not working. All right, let's do this problem and get the answer here. That's not going to help me because I need to know the numbers. There we go. I gotta scoot my chair forward here, so you gotta move out of the way. Now she's scared. Run away. Don't get squished. All right, so I have a block. And my block has mass 64.5 grams. I'm going to put this in a graduated cylinder here. And the graduated cylinder, I don't know, it's a little wavy, I guess, whatever. Has 75 milliliters of water in it. Now, when I put the cube into the cylinder, and now the cube is in here, this water level goes up and is now 82.2 milliliters. Because when you put something in a liquid, you displace the liquid by the volume of the object that you're displacing it, right? So whatever this difference is must be the volume of the block. And so we can do that calculation really easily. These are all in milliliters, so we'll just write that. So now I know what the volume is of this block. And I also know that a milliliter is the same as a cubic centimeter. So I can figure out the density. So the density is just going to be the mass over the volume. Which will be 64.5 divided by 7.2 is 8.958333333, which I'm going to write as this. And we'll explain why in the next section. And then if I want to figure out the edge length of the cube, well, I know that the volume of the cube is its length cubed. So if I take the cubed root of the volume, that'll be the edge length. So that would be 7.2 cubic centimeters. Now, if you don't have a cubed root button on your calculator, or you just don't know where it is, And this is the answer that I got. If you don't have this command, what you can also do is this. That's not a 3. There we go. So a square root is the same as raising something to the power of 1 divided by 2. A cubed root is the same as 1 over 3. A fourth root would be 1 over 4, and so on and so forth. So we can simplify that as, if you want to take the nth root of something, that's the same as taking that something raised to the power of 1 over n. And it's way easier to typeset that in the calculator, because all you gotta do is find the exponent button and then just type in parentheses 1 divided by 3. All right, there are our very simple density problems that we have there. We're going to make that a little more complex when we get to the end of Unit 1, and also, again, when we get to the end of Unit 2. But for now, we are at about break time because it is 12:50. So I'm going to go over to here and put this on the screen. Let me get the timer up. And we'll go back to listening to more Bravely Default, including the first song, which gets a copyright claim on my account, but like I don't care because it's so good. So, oops, hold on. That was the end of the last song. Where is it? There it is. Here we go. All right, we're back. Might as well let the song play out when it's at the end there, right? All right. Boop, there we go. This next section is all about sig figs, and hopefully we remember how to sig fig, because I'm going to go kind of fast through it since this should be review. The whole point of having to deal with sig figs is oh my goodness, my cat was just sitting here this entire time, and as soon as I start talking, it's Meow City again. The whole point of dealing with sig figs is because whenever we deal with a measurement and a number that is given to us that somebody used a tool to acquire, that measurement is going to be inexact. For instance, if I were to ask you, type in the chat what volume is in this graduated cylinder. Go ahead and do that, and we're going to see if we can show our point here. So this graduated cylinder, as shown, it has this part is zoomed in. Type in the volume that you think is in the graduated cylinder based on what you see here. All right, last call for guesses here. Or measurements, I should say. We're not guessing because that would imply random. All right, so a bunch of people wrote down a bunch of different numbers. Some people noticed that there was milliliters up here at the top, so that's good. But when we make a measurement, there's always going to be some degree of error in the last digit. For example, when I did this problem, this is the volume I recorded. Nobody recorded that. Does that mean that I'm the only one that's right, or does that mean that I'm wrong? Is chemistry a democracy? We voted 21.5. Yours is wrong. No, everyone's answer is right, right? And the reason for that is because it's kind of hard to tell. I mean, if I could draw a straight line, it'd be a little easier. It's hard to tell where this really crosses through the axis, right? Like, it looks halfway between, but could it be a little higher or a little lower? Well, sure. So if you wrote down something like this, or that, or maybe even this, I think all of those are good. But we would know better than to write 21.0, because it doesn't land right on the line. And we would not write 21.9, because that's way too close to the top line. So we can exclude some numbers, like 1, 2, 8, 9. Those are probably out, but there are a bunch of other options that are pretty valid for this tool. Now, it looks like everybody knows the rules on how to measure anything, but just in case you don't, here are the rules for measuring anything. Determine the two marks that any object falls between on your scale. So here are my two marks, this top one and this bottom one. I'm going to write their values here. This should say write out all of the digits of the image cut it off a little bit, of the lesser of the two marks. So the smaller mark was 21, so I'm going to write that down. And then I'm going to estimate the next one digit. So this is estimated. And these digits are known. And in this case, I estimated it to be 6. And then append the units to the measurement. So that's how we measure anything. You're going to use these 3 steps, and you must use these 3 steps. If you use some other technique, you will possibly get the wrong answer. And that's no good. We don't want that. All right. So on the board are 2 rulers. What I want you to do is for the first ruler, and I'm going to actually, we're going to go like this just because I can manipulate it a little easier here. So I'm going to put ruler A on the board. And what I want you to do is in the chat, type in the measurement that you should make for ruler A. Okay. Don't forget the units. The units in this one are posted on the ruler. All right, now that we've got a bunch of answers for ruler A, let's do the same for ruler B. Tell me the measurement you should make for ruler B. All right, very good. It looks like we are applying the rules correctly. Let me get this back on the screen so that I can use this later. And then we'll go over here. All right, so using the rules, I'm going to isolate the 2 marks that my object falls between. I'll write the smaller of the 2 marks, and then I will guess the next digit. So that's all I can write for ruler A. But for ruler B, I have much finer marks here. And so this is 4.5, and this is 4.6. So I could write 4.5 because I know those for sure. And then I guess the next 1 digit, which would be that. So as you can see, getting more marks allows you to write with more precision on the tool that you're using. Now, for physical objects, it becomes very difficult to get more marks onto a device without it becoming so impossible to see the difference between the marks or the resolution, without making something like really, 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 really long. So you could have a tube that measures microliters, but it has to be extremely narrow and long. And so we do have microliter syringes. It's just that they are very awkward to work with. All right. Now, if you have a balance and you're using a balance in the laboratory, all the uncertainty for the measurement is shown in the last digit here. So what this is saying is that if this was my balance, like there was a needle or something, and the needle was pointing right, say, here, and this one was 21.16, and this is 21.17, then the result that it would write would be 21.164 based on where the needle fell, 4/10 of the way between the 2 marks. Now, why it's measuring in ounces, I don't know. I just assume that it's grams. So all devices that have numbers operate on this principle. You have some sort of gradiated scale, and then you are going to fall somewhere on that scale where you are between 2 marks on the gradation. And based on your position, you can estimate where you are. And the scale does that to the best of its ability. However, that is still estimated, so we will have to note that when we're using that for calculations later. Now, the whole concept of where's my error is wrapped up in this concept of significant figures. So when we are measuring objects and reporting their numbers, their uncertainty will be carried along. Oh, excuse me. Sorry, I find sig figs boring, I guess. That uncertainty will be carried along in the measurement and then any operations you do with it. So we need to define what a significant figure is. It's any number that you know for sure, or you have estimated you have estimated to some degree of certainty. So that last digit that I've been guessing, so like instead where everybody said 21.5 and I said 21.6, that digit that we estimated, the 5 or the 6 in my case, that's our uncertain estimated digit because we've narrowed it down. So we can count that as significant. It is not a completely random number that we have chosen. So that makes it a significant figure. The more significant figures that you write down, the more precisely known a measurement is. So if I write down this right here, 21.1, that's not a very good measurement. That means the tool that I was using was kind of rudimentary. But if I were to write down this measurement, I used a much better tool than just a wooden ruler to get that number. Oh, I don't know why I have the yawns all of a sudden. What digits are significant? Any number that is non-zero is always significant. If you know a number, then you would write down its value. And so 1 through 9 imply that. 0 is interesting. 0 is sort of an edge case. If you know for a fact the digit is 0, then it counts. It's a sig fig. But if you don't know if it's 0 because of rounding or you're using it as a placeholder or whatever, then it's not a sig fig. Let's look at some examples with 0. So if I owed you this much money, $3,996, and then I rounded it to 4,000, and then said, well, wait, the zeros don't mean anything. They're just placeholders, right? So I could just do this. There, that's how much I'm going to pay you. I would be rightfully criticized for doing this, right? Like, that's bullshit. This is how Wes makes his money, is he scams people out of thousands of dollars by pulling some sort of mathematical trickery and philosophy on them. Like, no, that's not okay. You cannot do this. So what does that mean, though, for this example? Well, those zeros must have to have some meaning then, right? And the meaning that they impart is if I just have this 4 by itself, well, that's my 4 in the ones place, right? If instead I were to tack zeros on behind it, now that 4 is in the tens place. And if I do this, now it's in the hundreds place. And so on and so forth, right? So these zeros that I am imparting here to get my other number to be in the correct order of magnitude, these are my placeholders. Placeholders are necessary for our numerical system to work. However, they don't have any intrinsic known value because those zeros are implying that, oh, I've rounded something to the position that precedes the zeros. In this case, I rounded to the thousands place. So in reality, this number could be 3785, or maybe it's 4449. That would still round down to 4,000, right? And thus, this hundreds digit could be literally any number I want it to be. And so could the tens digit, and so could the ones digit. Since any number is possible based on that rounding, I would essentially be guessing randomly if I were to write down numbers. So we won't count placeholders as being significant. Placeholders are not significant figures. They are important because they adjust the magnitude, though, so we do still need to consider them. Now, a way to think of this is that if you take your number and you just black out or highlight away or whatever the zeros, and the value of your number changes. So, for example, I have 1,250,000 here, but if I do this, now I have 125. Those are very different numbers, so those zeros must be placeholders. The same thing happens if I have preceding zeros here in a decimal. This is a really tiny number, 0.00004386. Now I can make it a reasonably large number by removing the zeros, right? So those zeros must be placeholders because they control the magnitude and therefore the value of the number. And when a zero is used in that way, it is never a sig fig. If you have zeros that get sandwiched in between other zeros or other numbers, so these are all sig figs because they're digits. Any zero that is trapped in here is known precisely because if I know numbers after it, I must know the numbers before it, right? These zeros, however, are just placeholders because they could be round. Whatever number I actually had is rounded to this value. And because this is the third time I've done this lecture in a day, we did this discussion yesterday too. Do I still have the link that I've been passing around for this? I don't think I do. Hold on. Hopefully you recognize that number. And if you don't, well, here's a video that will explain. Can't play that on my YouTube because that is a classic rock song from 1982. All right. If we're working with numbers and a decimal is present, we must invoke this rule. This is called the decimal rule. If you see a decimal point, there you go. Follow these rules. Underline all the numbers that are non-zero. Bing, there you go. And then everything to the right is a sig fig. There you go. Everything on the left of the underline is a placeholder. Now, when does this circumstance occur? How do we know that these zeros are known? What has happened here is that we have landed right on a mark, more or less. So if you get extra zeros toward the end, it's because your measurement landed on a mark and the predicted number is 0. So that can happen. If I have a scale that looks like this, so 99, 100, 101, 102. If I were to do this, I would guess the next digit after I wrote down. So my marks are here and here. I would write down the known number, so I know it's 100 because that's the mark I'm on. And I guess the next digit. And there we go. So now I have a bunch of zeros in my answer, but those zeros are actually known because that's where my device measures to. So this can happen. Just be mindful of that possibility. And the way that we preserve those zeros as known is we invoke the decimal rule. If there is a decimal point, all of the trailing zeros now become sig figs. And it doesn't matter where that decimal ends up. All right, here's more examples here of how many sig figs there are in each of these numbers. Oops. I thought there was another blurb at the end of that. All right, you can always pause or rewind the video to refer back to this, but what I want to do is put the examples on the screen here. I want you to treat each of the numbers in the top part of this, where you count the number of sig figs. I want you to treat each of those as if they were something you measure. I realize that you don't measure XP. Like, that's a discrete entity that you hand out. You don't hand somebody 1.7 experience points. Actually, if you do, you're like the most ridiculous DM ever. And I don't mean that in a positive or negative connotation. I just think that that's kind of crazy. But anyway, assume that these numbers are all measurements. And what I want you to do is tell me the number of sig figs in each number as shown. And then on the bottom, what I want you to do is tell me what the correct measurement is for each graduated cylinder, with the assumption that the bottom of these two cylinders is 0, and that this line is here for some reason that I don't know. It doesn't mean anything. I'm going to give you about 3 or 4 minutes to do this, and then we'll go over the answers together. See you in a bit. When you have your answers, by the way, type them in the chat. All right, 1 more minute, we'll go over the answers. All right, so let's look at these numbers as written here. So 900, let me get a different color for my pen. 900 as written has just one sig fig because the other two zeros are placeholders. If I scribble out these zeros, I get the number 9, which very different from 900. Although only needing 9 XP to reach level 2 would be kind of nice. Or level 3, I guess. This right here, 90,210. That's not how we say zip codes, but as written, oops, that's pretty bad. As written, this number has these 3 are digits, so they're non-zero digits, so they are significant. This 0 is trapped, so it must be known, but this 0 on the end here is a placeholder, so there are 4 sig figs total in this number. For the mass of this flea right here, I have 2 that are non-zero, so they definitely count. I do have a decimal, so everything to the right is significant, and everything to the left is not. So there are 3 sig figs in this one. And then 500, watch out, there's a decimal here, so the same rule applies. So this 5 is significant, and then everything to the right of it is also significant. So there are 3 sig figs in 500 dot milliliters. So, very important distinction here. This number has 1 sig fig on the top, but this bottom one has 3. And that dot is what makes all the difference. So, be mindful of that, because that's an easy issue to run against. For these graduated cylinders, this should be pretty straightforward. Measure between these, so this is the lower end, 500 something. I'll guess the next digit, which would be 540 something, and then I had to include that something. Here, same thing, so 540 something is my low. I'm going to guess the next one. I'll say 5. That's good. But this first one, you have a very interesting sort of situation here. And so if you started with just your first digit as 0 and then guessed the next digit, you'd be in the decimal point range, and that's kind of weird, right? The volume of this is definitely not 0 point something. So how does this work in terms of guess the next digit after our mark if the first mark is 0? Well, you could think of this as being, well, if these measure every 1,000, I could have 0,000. This would be the number I know, and then this would be the next digit I guess, the hundreds place, which I would then guess to be 5. And then that's how you would get this value. I have 0,500 because my mark for the first mark is 0,000 as opposed to just writing 0. Now, of course, we're not going to label the marks as 0,000 or 0,100 or whatever, because that's extraneous and nobody writes their numbers like that. But it is good to think of it that way. All right, any questions? Let me know in the chat. Now that we have discussed sig figs and reviewed them, we're going to do math with them. And we should all remember how to do math with sig figs, but here's some examples just in case we want a refresher. We're going to separate these into 2 types of operations. There are more than just these 2 types of operations, but these are the 2 that we're going to be doing in this class. And all of these types of operations have their own set of sig figs rules. So the first set of rules applies to addition and subtraction. The second set applies to multiplication and division. There are sig figs rules for logarithms and exponents independently. But we're not going to worry about that in this class, and you probably won't learn those in 162 or 163 either, because by that point we don't care. Why is B not 550? I wrote 540 because I thought it was slightly below the midpoint, but if you wrote 550, that would be okay. Because remember, this digit right here, this is our estimated digit because we don't really know with certainty where that's falling. Like, how I drew that, it makes it look like it's in the middle. But to me, looking at the blue, it looks like it's not. So it's hard to say. There's uncertainty. So either answer should be correct. All right, let's do the addition first. When you do addition, remember that in a measurement, any numbers that come past the last significant figure are essentially random, right? So when I measured this object to be 352.8, we'll say kilograms or whatever. These next digits are not all zeros. That doesn't make any sense. Like, the odds of that happening are essentially zero, right? So when I have digits that precede my known sig figs, they're assumed to just be question marks. Because they can be any number that we can think of, really. And now when I do addition here, I could say, oh, well, question mark plus 1 plus question mark is not 1. It's actually just question mark, right? So when I do these addition problems, I'm not going to get to keep these numbers. I should still do the addition because any rounding that happens here may affect our result later on. But any position that has a question mark in a column when I'm doing the addition isn't going to get kept. My answer is going to stop right there. So here's how we're going to do addition and subtraction. Whenever you do addition, you need to set it up vertically. Subtraction, you need to do this too. But subtraction, you do one at a time. Here, I can add multiple numbers together. So I'm going to do that addition. Oops. Let me just do that addition really quickly. So 1, 2, 9, 5, 3, 5. Is that right? Okay. So there's the addition that I got for this problem. I'm going to then put in my blanks. And what I'm going to do is I'm going to start from the place that is furthest to the right. So that's here. And what I'm going to do is I'm going to ask myself, is in this place, the furthest place to the right, is there a known digit in every value? And the answer is no. I have question marks here. So I don't get to keep this number. We'll go to the next one. Do I get to keep this number? 8 plus 4 plus blank. No, I don't know what blank is, so I don't know what that number must be. But over here, 8 plus 6 plus 4, that totally adds up. And that could be an 8 or a 9 if something carried over from the previous column. So there we go. There's my answer, 535.9. We're going to round to that position because that's the first spot coming from the right that all values have a sig fig in. All right. Let's do another example or two, and then I will give you some... well, actually, I'm going to do multiplication, then I'll give you some to try. So if I was to do this problem here, first we got to erase all this. We're going to set up the problem. I'm going to just do the subtraction as normal. And then I'm going to start from the right, look at each position. Can I keep this number? Is there a significant figure in every position? No, there's a blank here, right? So I don't get to keep this one. How about here? That checks out. There's a number in every position. So the answer that I would report would be 4.1. I don't get to keep that 3 because there was no digit in the hundredths place for 0.7. All right, how about this next one here? This is where the numbers start to get a little bit unusual, and you start to get bogus results, or at least it feels bogus, but the system is set up in a very specific way. All right, I'm going to add these two numbers together. So all this just carries straight down. And then I can add these two. Now I'm going to go check to see how many digits I get to keep. And so looking here, well, these are all going to be blank. So nope, nope, nope. But what about here? There's a 0 written there, but is that 0 a sig fig? No, it's a placeholder, right? So I don't get to keep this one either. Or this one. It's not until I get to here that I can report the answer. Now, you cannot report this as the answer, because 7,300 plus 139 is not 74. That's way too small, right? You need to append the zeros yourself as the placeholders so that you get the correct magnitude of the answer. Okay, so this is the correct answer, 7,400. And that is going to lead us to this problem, which is really obnoxious. When I add these two numbers together and follow the rules, these are all placeholders, and I don't get to keep these numbers. And so in this class, 3,000 plus 6 is 3,000. And this is where a lot of first quarter students go, what the hell? That's absurd. But in reality, this actually makes a lot of sense based on how we're using estimates and tools. Let's do another example here. Let's suppose that you win the Mega Millions and you win $675 million. That's a lot of money, right? But you're new to this millionaire thing, and so you celebrate in the only way you know how. You're going to go buy a Big Mac for $6.99. How much money do you have on you if you're carrying the $675 million around on you or whatever after buying your Big Mac? Would you have 674,999,994? Or do you just say, I don't give a shit about these numbers no more. I have $675 million. And that's exactly what happens. We do not give a rat's ass about this number. You could drop $10,000 on something, and that millions digit right here wouldn't even blink. You could do that in the hundreds of thousands of dollars digit. Go spend $100,000 on something. That number won't even blink. This is why we want to tax the hell out of Jeff Bezos. When you have hundreds of billions of dollars, you could drop $1 billion and not even notice it. And the reason that you don't notice it is because the magnitude of these two numbers is too far apart to affect each other. Let's do another example with a visual here. So you work at the jelly bean factory. And so these are jelly beans. Those are the biggest jelly beans I've ever seen. But anyway. And there's thousands of these things. So there's 50,000, 40,000, 30,000. And then so on and so forth. And this must keep going down because otherwise it scales weirdly. Anyway, you could estimate the number of jelly beans in this bin, and it'd be about this many. And then let's suppose it's the night shift, and you're there all alone, and you sneak into the jelly bean bin, and you go, "Hump." You eat it. You eat as many as you can, which is like 20, right? Because who the hell eats thousands of jelly beans? I'm not judging you if you do eat thousands of jelly beans. I'm just implying that at once on your night shift, probably not going to eat 1,000. You're probably going to eat just a little tiny bit. And you're barely going to notice it at all. So when you go and do the math, nothing happens. These numbers aren't going to be kept anyway. So if the magnitude is way too different with addition, you get bogus results. Or at least they look bogus. But in reality, they actually reflect what we know about the number. Okay? So don't freak out if you do a problem and you get the same answer. Oh yeah, Kirby's different. If Kirby ate all the jelly beans, I would believe that. And he would just smile. All right. What I want you to do is take your notes and draw a big line through it. Some sort of partition to isolate the addition rules from the multiplication rules, because I don't want you to mix the two up. If I am making a measurement with a tool, and the quality of that tool is good, using that number in operations will produce good data. But if the quality of the tool is poor, then I get poor data regardless of the quality of how good my other data is. An analogy for this would be, say, I'm going to make chicken enchiladas for dinner. So I'm going to cook the chicken, and I'm going to season the chicken breast. We'll dice up some onion. We'll get the green chili sauce. Put some jalapenos in there. Fry up some tortillas, and we'll put it all in the tray. And then I'm going to top it off with, all I have is rotten cheese. Rotten, moldy cheese. Everything else is fine, but all I have is rotten, moldy cheese. Well, you can't have enchiladas without cheese, so I'm going to do it anyway. What is my dish going to taste like? It's going to taste awful, right? Because I've used moldy cheese. It's going to taste like mold. Doesn't matter how good the other ingredients are. The shitty ingredient ruins everything, yeah? Multiplication is the same sort of issue. If you have a really crappy number, you get a crappy result. And the reason for that is if we did long multiplication involves this part where you add up a bunch of things together, right? Well, when we're doing the multiplication, you're going to get a bunch of question marks, which are blanks. And those blanks will propagate through your equation as you're going. And then you can only keep stuff from this point forward. And the fewer sig figs you have in one of your multiplicands, I think that's what they're called, multiplicands? The fewer sig figs you have, the fewer you're going to get to keep at the end, because everything else is going to be question marked away, right? Now, we're not going to do long multiplication. That's just the theory behind it, so we don't need to do this. What we're instead going to do is just summarize it in the following manner. For each number that is going into the multiplication or division operation, count the number of sig figs it has. So this top number here, 14.2985, has 6 sig figs. This second number here, 6.4, has 2 sig figs. Then when you do the multiplication, your answer will have whichever number you wrote down is smaller. So which is smaller, 6 or 2? Well, 2 is smaller, so my answer must also have 2. So I'll punch that into the calculator, and I'll get whatever number I get. Here it is. I must now round to 2 sig figs, so I'm going to just keep these 2. And that would be the number I report. I'm rounding to 92 because the next digit after the digits we keep is 5 or greater. We're not going to do bankers rounding in this class because, again, we're only working with one operation at a time, really. We're not taking an average or anything, so we don't have to worry about round to even saving us a little bit of error. If we're just doing one data point, round to even will introduce more error than it saves. All right, so that's how we do multiplication and division. Division is exactly the same as this. You're just going to count the number of sig figs. So this problem, I can literally just type in on the calculator, 5.4336 times 1.2, and this is the number that it spits out. But how many sig figs should I keep for my answer? Well, if this one has 5 sig figs, and this one has 2, then I should only keep 2. So I would expect that the answer should be 6.5. All right. Division, exactly the same thing. Punch it in your calculator, then worry about sig figs later. So I got here 91.6736841. That's way too many sig figs. This is 5. This is 3. So my answer should have 3. Now, the same thing sort of happens if you have a ridiculous disparity in the number of sig figs in your values. So if I do this problem here, I'm going to get a very crude approximation. 7.63829 divided by 2 is 3.819145. But what I'm forced to do here is to round to 1 sig fig because this is the fewer of them. This one has 6 sig figs. And so I would have to round to this position. So I must report this as my answer. Which is very, very bizarre. But if you reduce the quality of one of your measurements, you reduce the quality of your answer. And that's no good. Excuse me. Now, there is one other issue to address, and that is what happens if you have an exact number? Exact numbers have infinite sig figs. And the reason for this is if something is exactly 2, it would be 2.0000000 forever, right? This goes forever and ever and ever. And if you count the number of significant figures, there are infinite of them. How do I indicate to you that a number is exact versus inexact? Assume all numbers are inexact unless I have indicated otherwise. And the way that I usually do that is I will say the underlined number is exact. And in that case, you just have to be sure that you don't treat it as a one-digit number and reduce everything to 1 sig fig. That's going to help us out on Wednesday when we start doing conversions, because our conversions are always going to have an exact term, and it's going to be the thing that says one of these, exactly one of these, is this many of this other thing. Last warning that we have is that if you're using a calculator to do these types of problems, your calculator doesn't know what sig figs are. If you do this equation, or calculation, I should say, in your calculator and hit enter, you'll get some number. Report that number in the chat, and I'm going to do this the long way. And we'll check to see I get to keep that, so this is the correct answer. But if you did this on your calculator and typed in the result, what do you get? You get some number, but it has way fewer sig figs. Yeah, it's 8, right? So this is what your calculator says. The calculator answer is just 8. And it actually may have a dot after it. It doesn't really matter. What your calculator is doing is any zeros that are at the end of your answer, it just deletes. It thinks that they aren't relevant because you don't need them. They don't have a value associated with them. This is where the $3,996 rented to $4,000 thing comes from. Your calculator just removes any extraneous information that it doesn't need because it's programmed very simply. However, in some cases in science, we do need those zeros. So just be mindful of that. Don't rely on your calculator to do sig figs because it will do them wrong. All right. Now, there is an issue that comes up if you try and do multiple operations together. And that is, well, what's the answer? What's the correct number of sig figs? Well, first we need to do this. We all remember what this is, right? This is please excuse my dumb ass sibling. Or in other words, parentheses, exponents, multiplication, division, addition, subtraction. That's how we learned it, right? No, that's totally not how we learned it. I made this up like 4 years ago. I've never heard it anywhere else, but I think it's more amusing. And then you won't forget it this way, right? All right. We have to do operations in this order. This is the order of operations, right? So according to this on the expression up at the top, I should do the subtraction first. Then once I've subtracted, I can take the result and divide by the other number to get the answer. So what I'm going to do is every time I do an operation that I know the rules for sig figs for, I'm going to just manage that and do it all the way to the end of that operation type. So in other words, I'm going to do subtraction, carry out the correct number sig figs, then go import that value back into the calculation, and then do the next operation and follow its rule, import that into the calculation, and just keep doing that until I'm done. So let's show how that works. So the first operation is just subtraction, right? So when I do my subtraction, I get that. But using our sig figs rules, these first two positions have blanks in them, so I don't get to keep them. So this is the number that I get as a result, which I'm going to import up here. Notice that the number I got for my result does not have the same number of sig figs as any of the other numbers do, and it ends up governing the number of sig figs that I have at the end. Because now we're doing division, and a 2-digit sig fig number divided by a 4-digit sig fig number is a 2-digit sig fig number. This is the part that gets Chemistry 161 students, is you look at this and you want to apply the multiplication rules to everything because it's the easier one, right? And so you do the subtraction and then you don't notice that, oh, that subtraction reduced or increased the number of sig figs I have. If it was addition, it would increase. Addition and subtraction are weird. They modify the number of sig figs because they don't care about how many sig figs you have at the start. They just care about places. Multiplication and division do care about the number of sig figs, and they don't work well together. So you have to be very vigilant that you're doing the correct operation in the correct spot. Okay? Be careful, because the questions on Canvas will definitely take advantage of this, and there's some stuff in the lab that is important too. And I just realized we forgot to go over the lab. Well, that's okay. I guess we'll just do the lab at the start of the period tomorrow, and if I run out of time then, I'll make a video about it. The lab is very straightforward. Really, the explanation is just read all of the stuff about the glassware, and then you're going to be trying to figure out what volume of water is weighed out versus what volume is measured out, and compare the two. You're going to use the density of water to figure out the mass, or you use the mass and the density to figure out the volume that's weighed out, and then compare it to the marks in the containers. But I'll go over that in a little bit more detail tomorrow. I don't want to keep going because it's 1:55 and class ends right around now. So I'm going to leave these practice problems here for you to do as a sort of like homework exercise. We'll start tomorrow by going over these answers. And then we'll finish chapter 1 tomorrow, which means that there will be a quiz available. So don't worry about anything just yet. There is a lab that is coming up next week, but you'll have plenty of time to do it because we'll discuss it tomorrow. I do want to thank everybody for coming out to the lecture. I don't really have much to say because nothing is due coming up other than quiz number 1 will be posted soon once we finish the chapter. I know I was getting a lot of emails about that. But yeah, don't worry. Nothing has been posted yet. Nothing is due yet. So everything is fine. But yeah, that's all we're going to do today. I will see you tomorrow. Go out and enjoy the sun. Have a wonderful spring day. What are you still doing here? Go outside.